All right, good afternoon. How are you all doing? Good. A lot of people getting an early start on the weekend. All right, let's see. Well, let's uh, let's continue our journey on AC sinusoidal steady state analysis. So we stopped here last class. All right, so we covered the complex number representation for sinusoidal waveforms, whether it's voltage or current, and then we also looked at impedance, right? And we looked at impedance triangle. Any questions about any of those concepts? Again, as a reminder, the reason we are using complex numbers for representation is because it makes the math less complex. And we will solve a few examples today where we'll go through the process and you'll be able to see for yourself. Right? Okay. So just wanted to point out something on this slide. Let's see. CL, Excel, I think we covered all of this. Oh, yeah. The mathematical representation of impedance in rectangular coordinates, we say it's R plus JX. And we say R is the real part of impedance, the resistance, whereas the reactance is the imaginary part of the impedance. Now, when you read the words imaginary part, or where someone says reactance is imaginary, well, we are only referring to the mathematical representation. Reactance has a physical basis in real life, right? It is the energy stored in the inductor and the capacitor that opposes the change in the current or the voltage. So it is not direct opposition. For an inductor, if you have current passing through the inductor, it's a coil of wire, right? So it just passes through without any problem. In real life, the inductor resistance might be a few ohms, like 1 or 2 ohms. If it's a really good quality inductor, it'd be even less than 1 ohm. Bad quality inductors, you have some high resistance. In theoretical analysis, inductor resistance is equal to 0, right? So it's simply a short circuit, allows the current to actually pass through. Energy is stored. That energy creates generates a back EMF or a voltage that opposes the initially flowing current. And so if you try to change that current, that stored energy is going to oppose any change in that current. So it's not direct opposition. So resistance is equal to 0, but any opposition thereafter to oppose any change in the current is represented as the reactance. So it has a physical basis in real life, but mathematically we say it is imaginary. Does that make sense to everyone? Okay, so whenever you read the words imaginary reactance, it is not something that's just coming out of thin air. Okay, it's a mathematical representation that is imaginary. So for a resistance which does not have any energy storage, reactance is equal to 0. Okay, for a resistance, reactance is equal to 0. So if we write ZR would be R plus JXR, sorry, XR, and there is no such thing as XR, and so ZR is therefore equal to R. And ZL, as we see up here on the right, is actually, we have the equations, but let me write it out here. ZL would be the inductor resistance RL plus JXL. RL for an inductor would be equal to 0, and hence we can write impedance of an inductor is JXL, where XL is omega L. So this becomes JXL, and XL is omega L, or 2 pi FL. Similarly, ZC would be RC plus J, or actually 1 over JXC. RC is actually infinite. This simply becomes 1 over JXC. If you'll remember, capacitance has two plates separated by an insulator, so represented by a resistor of infinite resistance in parallel with that capacitor. So when you have it in parallel, ZC would actually be 1 over the reciprocal. You're adding up the reciprocal. So when you add up the reciprocal, that goes to 0. But the point is that ZL is JXL, ZC is 1 over JXC. Okay, impedance of an inductor and capacitor is basically the reactance or the imaginary reactance. The reactance is the impedance without the J representation. Okay, the math that we need to do. Actually, let's go to, before doing the math, let's go to the fundamental laws. So we've studied the laws in chapters 1 and 2, right? And the analysis techniques. Ohm's law is V equals IR. KVL is simply sum up all the voltages in a loop and you get 0. KCL is the same way. You add up all the currents entering and leaving a node, they should sum up to 0. So all of these laws work for sinusoidal analysis also. The only thing is, everything is represented as a complex quantity. So VR is I times R. The resistor current times the resistor. VL is IL times ZL. VC is IC times ZC. So Ohm's law still works. Ohm's law will work. KCL will work. KVL will also work. Everything works exactly the same way as we did, except that all quantities are now in complex numbers. So all quantities complex numbers. Some of you have taken the lab, right? Lab 6. Do you all remember lab 6? Phasor diagrams, where you measure the voltages across the inductor and the capacitor and the source. If you added up those voltages, it did not make sense because it did not equal Vs. And the reason is we are simply adding up the magnitudes. We are not adding up or taking the phase angles into account. So when you have a complex quantity, when you have complex number, V1, V2, V3, they have magnitude and they have phase angles. If we just measure with the meter and try to add up V1, V2, and V3, they would not work because we are not adding up or we're not taking the phase angles into account. So in order for all of these laws to work, we need to take the phase angles into account in our math. Otherwise, they would not work. And again, I've repeated that statement where I say that the use of complex numbers is so that we can make the math less complex. And we will solve a few examples today and you will see exactly how and why. Impedances add up the same way that you add up resistances. So impedances add up the same way as resistors. Add up the same way as resistors. So if you have 2 or more impedances in series and you want to find ZEQ, the total equivalent impedance between any 2 points, you simply add them up, Z1 plus Z2 plus Z3 and so on and so forth. If you have multiple impedances in parallel, you simply add up the reciprocals of their, you take the reciprocal of the sum of the reciprocals. So 1 over Z1 plus 1 over Z2 plus 1 over Z3 and so on and so forth. Okay. Now, when you have 2 inductors in parallel, what do we do? If you want to find one single inductance between those 2 points, if they're in parallel, what do we do? We take 1 over L1 plus 1 over L2, and we take the reciprocal, right? If we want to find the total impedance of those inductors, what do? We'll do the exact same thing. 1 over ZL1 plus 1 over ZL2, and we take the reciprocal. What if you have capacitors? Two capacitors in parallel, C1 and C2. If you want to find the total equivalent capacitance, CEQ, what do? Yep, C1 plus C2, right? But if you add up the impedances of those very same capacitors, you would have to use this equation. So it would be 1 over ZC1 plus 1 over ZC2. So the example I want to point out is this. You have a capacitor, C1, C2, and you want to find CEQ and ZEQ between those two same points. So CEQ would simply be C1 plus C2, but ZEQ would be 1 over ZC1 plus 1 over ZC2 and the inverse. Does that make sense? Take 10 seconds and think over it. Let me know if you have any questions. Any questions? Yes. Absolutely. So that is going to be my next point. We have resistors, inductors, and capacitors, 3 different components. If you have them in series or if you have them in parallel, we cannot combine them, right? We cannot say inductor plus capacitor equals 1 inductor or like 1 capacitor, 1 resistor. But we can combine their impedances together. So if you have a resistor and an inductor, RL, or you have RC, or you have RLC, we cannot obviously combine them. They're physically 3 separate components, but we can combine their impedances together. So if they're all in series, we can say R plus ZL plus ZC, or if they're in parallel, we could say 1 over R plus 1 over ZL plus 1 over ZC. Make sense? Right? We cannot combine the components, but we can combine your impedances. And that is how we would solve circuits. That is how we would solve circuits. Does that make sense? Any questions? Okay, just want to point out some concepts of reciprocals. So oftentimes in circuit analysis, when we have parallel circuits, it makes it very complicated because you're working with reciprocals all the time. So they came up with these concepts of reciprocals of the quantities that we're working with. So for resistance, and I believe we talked about this early on in chapter 1, I mentioned it like probably once. And you may also have learned it in physics probably. The reciprocal of resistance is conductance, right? We started off there. We have like a conducting wire that allows the passage of electrons. So current is flowing through, right? It allows the electrons to be conducted or to flow through the wire itself. Any opposition to the flow of electrons is termed as resistance, right? So we began there. So reciprocal or the inverse of resistance is conductance. Similarly, the reciprocal of reactance is known as susceptance, and the reciprocal of the total impedance Z is admittance. They are represented respectively by Y, G, and B. Units of impedance, resistance, and reactance is all ohms, whereas the units for Y, G, and B are all Siemens. Okay, named after the German physicist Siemens. Now, in EE major classes, I would actually solve an example so that students can actually see how and why it is easier to work with these reciprocals, right? If let's say you have 3 resistors in parallel, you're trying to analyze for the circuit, right? And you want to perform current division, for instance, let's say. If you have conductance, you already have 1 over R1, 1 over R2, 1 over R3. Then if you want to find the total conductance for the circuit, all you do is you simply add them up, G1 plus G2 plus G3. And you can also perform current division directly just by applying Ohm's law. Okay, again, so if this was an E major class, I would solve an example and show you exactly how and why working with reciprocals is easier. But hopefully that little explanation makes sense, right? You have 3 resistors in parallel. If you're working in conductance, then you would simply add up the 3 conductances as if they were in series. This is not something that we'll look at in detail in the chapter, but at least you should be familiar with these concepts. Okay, any questions? Anyone? All right. So let's go back here. Here I stated that, well, this is the equation for the impedance of an inductor in rectangular coordinates. It's J omega L, right? Imaginary part. In polar coordinates, it is omega L with a phase angle of plus 90. ZC similarly has a phase angle of minus 90. So where does it come from and what does it represent? Well, for voltages and currents, we learned about phase, right? We learned about phase and phase shift. We learned about phase and what it represents. What does phase represent? It represents the moment in time when the voltage or the current waveform crosses the x-axis, right? And the distance between that crossover point and time t equal to 0 gives us the phase. If it crosses the x-axis at time t equal to 0, then the phase is 0, right? The phase is 0. If there is a shift or there's a difference between time t equal to 0 and when the waveform crosses the x-axis, that is defined as a phase shift. So for an inductor, if you plot the voltage and current waveforms, if I plot, if this is VL and I plot IL, there is a phase difference between the voltage and current for an inductor. And the difference is 90 degrees. The difference is 90 degrees. So again, the voltage and current for an inductor has a phase difference of 90 degrees. Which quantity is ahead? Voltage or current? Remember, this is the future. This on the left is the past. So voltage comes first, then comes current. So voltage is ahead of the inductor by 90 degrees always. For a capacitor, it's exactly the opposite. So for inductor, voltage is ahead of I. Now, without going into too much physics or too much detail, that's that's the explanation. And I is ahead of V by 90 degrees. Okay. Now, the mnemonic that helps us remember this. Eli the Iceman, named after Eli Manning. Anyone know who Eli Manning is? He's a quarterback for the New York Giants, won 2 Super Bowls with them. But ice in his veins. Not really. This predates him by many decades. It's probably been in use since before he was born. What does L stand for? Inductor. C, capacitor. I is current. E stands for electromotive force or voltage. So for an inductor, voltage is ahead of current, or voltage comes before current. For a capacitor, current comes before the voltage. Eli the Iceman. So again, as I said, it's been in use for many, many decades. There are other mnemonics too, but this one is the easiest. And so if you perform mathematical operation V divided by I, or ZL, right? Z is V over I. Ohm's law, V equals IZ, so Z is V over I. V divided by I always gives you a plus 90 phase difference. And ZC similarly would be V divided by I, but I is ahead by plus 90, so it becomes 0 minus 90. And so ZC will always have a phase shift of minus 90. Does that make sense? Now, when we say there is a phase difference between the voltage and current, we are referring only to that particular component. Okay, if you take one single inductor and you compare the voltage and current for that inductor, that will have a phase shift of 90. If you take the voltage of one inductor and you compare it to the current of another inductor, that phase difference or phase shift could be like 13.5 or minus 8.9. Could be any number, depending on how the circuit is configured. Okay, so this phase shift is only valid for that particular component. So if you take a capacitor, for instance, then the current will always be ahead of the voltage by 90 degrees, or the voltage will be behind the current by 90 degrees, minus 90. But if you compare two different components together, then the phase shift could be anything. So keep that in mind. So lots of students sometimes when they solve problems, they say, shouldn't the phase difference be like 90 degrees? Well, no, because it's two different components. You have to consider that you're only looking, I mean, this is only valid for that particular component, not with respect to anything else. Okay. Does that make sense? So if the inductor and the capacitor were in series, and we will solve a problem in this chapter later on, where you have a series RLC circuit. If it's a series circuit, what happens? The current is the same for all, right? The current would be the same for L and C. So if the current is the same, then the voltage for that inductor would be plus 90. The current for that same capacitor would be minus 90. So the phase difference between the impedance of a capacitor and inductor would be exactly 1/8. Well, I can't bend my arms that way, but not plus 90 and minus 90. Does that make sense? What do we have? An exact phase difference of 180 degrees. Okay, 180 degrees. But that is only if they share the same current, right? If they share the same current, then you could have 180 degrees. If it's something else, if it's a different circuit configuration, whether it's in parallel or series parallel, parallel series, then it would be something else. If it's a series component, it shares the same current, then you can have a phase shift of 180 degrees. Okay, questions? Any questions at all? Any questions at all? All right. So then we come here, polar to rectangular, rectangular to polar. This is something that I already have on my handout. Okay, the handout that's on Canvas. I hope students did look at it. We have a vector. Vector has a length of r, phase angle theta with the real axis. So r with the phase angle theta. The projection of that vector on the real and imaginary axis gives us the rectangular coordinates. The real axis projection gives us the real part A. Projection on the imaginary axis gives us the imaginary part B. Positive phase angle gives us positive imaginary axis. Negative phase angle gives us negative. Now, you need to perform mathematical operations, right? We are going to do V is equal to IZ. We might do V1 plus V2 plus V3, and these are all complex quantities. So we need to perform addition, subtraction, multiplication, division, whatever the case may be, depending on what a circuit looks like. Again, my calculator can transform rectangular coordinates to polar and polar to rectangular, but it cannot perform any higher level math than that. So, and I'm just going to do this briefly here. If you have two complex numbers and you need to multiply them, let's say R1 with a phase angle theta 1 and R2 with phase angle of theta 2, magnitudes are multiplied together and phase angles get summed up or added up. If you are dividing two complex numbers, then magnitudes get divided and phase angles are subtracted. So when you find impedance, impedance is V over I, V divided by I. So for impedance, it is always theta V minus theta I. For an inductor, V is plus 90, and so ZL, hence ZL always has plus 90. And if I am summing up two complex numbers, then I would perform that math in rectangular coordinates. Simply add or subtract the real parts together, and you add or subtract the imaginary parts together. Oh, yes, C, sorry. Any questions? Any questions at all? Now, if you have a programmable calculator, and again, when we get to solve problems, I want all of you to take out your calculators and solve it along with me. You would not need to perform all of these. But again, as an engineering student, you should definitely be familiar with how to do these. So fundamental laws, impedances, covered this. All right, examples 1, 2, 3, 4, 5. We'll try to get at least 1 through 4. 1 and 2 are exactly the same. So I will solve 1 and I will assign example 2 as a student practice. So first one, what is it asking us? It's asking us to find Vs of t. Okay, Vs of t. Meaning we are supposed to use phasor techniques and reduce this expression down to one single quantity, find the magnitude and then the phase. So first step, excuse me. We said we need to solve this with phasor techniques. What do we need to do in order to write a phasor? Cosine. So sine of x is equal to cos of x minus 90. So if you have 10 sine omega t, this becomes cos of omega t minus 90. Perform this maths on your calculators. What do you get? You're engineers. You should always have your calculator tied to your hip at all times. Keep in mind, we need the answer as a time domain expression. So final answer should be in polar coordinates. We need the magnitude and we need the phase. What do you have? What do you all have? You're not going to lose any points. Come on. Anyone? What did you all obtain? You see lots of calculators out, but tells me that no one practiced. Again, as engineers in your own field, you need to be proficient at using complex numbers. Anyone? No one? How much? Well, we need polar coordinates. We need polar coordinates. Yep. But you need the final value. 10 angle 0. If you want to plot that vector, you find the angle. Angle is 0, the length of 10. So it's right there. Then 10 with the angle of minus 90. Find the angle first. Minus 90 is pointing straight down. Again, length of 10. When you have 10 here and you 10 here, the resulting vector will always be at an angle of 45 because it's a right angle isosceles triangle, right? So angle will always be 45. And because it's minus 10, it's pointing in the fourth quadrant. So minus 45. I mean, that's basically the concept. That's the concept, right? I mean, you can visualize in the complex plane, real and imaginary axis, but then the math is not always going to be this simple. As long as you understand the concept, you can do the math using a electronic device. So this is 0 degrees, length of 10. This is minus 90. Again, length of 10. Does that make sense? And you're projecting this on the real axis. Of course, this is the projection on the real axis. This is a projection on the negative imaginary axis. So the resulting triangle would be the intersection of these two right there. And because they're both 10, the vector, of course, would intersect right there. The length of the vector would be root of 10 square plus 10 square. So you get 14.14 and minus 45 degrees. Does that make sense? Right. Again, become familiar with the concept. As long as you understand the concept, then the math, of course, is, well, that's different. So again, trying to repeat the same thing. You as an each individual student needs to be an expert in using your own calculators. That is not something I can help you with. I don't own a programmable calculator. And even if I did, your model would be different than mine. This is not something I can help you with. As an engineering student, you own your own devices. You need to be familiar with how to use those. Okay. So 14.14, this actually is the phasor Vs. And I go back into the time domain, perform the inverse phasor transform, magnitude. It'll always be cosine because we first go from cosine into the frequency, into the phasor form. So going back into the time domain, again, it is cosine. Frequency remains the same. That does not change. Minus 45 degrees and volts. That's the final answer. Okay. Does that make sense? Now, again, as I said, if you have a programmable calculator, you can go directly from here to here. You don't have to jump through all of the other hoops. Example 2, design as student practice because you solve it the exact same way, no difference whatsoever. Oh, by the way, this polar to rectangular conversion that I performed here in step 1, and then going from this rectangular to polar conversion, that I performed on my calculator. All engineering or scientific calculators are able to perform this basic function, going from polar coordinates to rectangular and rectangular to polar. Again, the maths, I mean, the concept is simple. They are the three sides of a right angle triangle, right? X and Y, real axis, imaginary axis, hypotenuse of the triangle, tan inverse of the two sides. So the concepts, again, is not something that's different. You would have learned that in calculus very early on. As an engineer, you would encounter this again and again and again in your own fields. So those conversions, polar to rectangular, rectangular to polar, I performed on my calculator. And then I just simply added it up. The answer for example 2 is 29.77 cos of omega t minus 40.01. And of course, the answer is false. Exact same manner, exact same procedure. Here the phasor is 20 with the angle of minus 45. Here it would be 10 with the angle of minus 30. Right, 60 minus 90 gives you minus 30. You have two complex numbers in polar coordinates. Add them up. And that's it. Questions? Any questions at all? Anything that seems off or any concerns? Anything that's not clear or easy enough? I just have one nod. Everything else, everyone else is just nodding off. Okay. All right. Examples 3 and 4. So examples 1 and 2, we learned, we simply looked at what we need to do to add or subtract sinusoidal waveforms. Here we are applying a voltage to a inductor and a capacitor. Both problems are very similar, no different. We don't need to find VL of t or VC of t. It's already given to us. Okay, so inductor is 0.25 Henry. Voltage across the inductor is given to us. We're asked to find the impedance, the current in the phasor, as well as in the time domain form. Okay, so what do we need to do? Well, first things first. Anytime you're faced with a problem, you always extract as much information as you can. So in this case, we will compare the sinusoidal voltage to our standard form of sinusoidal expression, which is Vm cos of omega t plus or minus theta. And we obtain Vm as 100 volts. Omega is 200 radians per second. And theta is 0 degrees because, well, it's already 0. This is already given to us in cosine form. If it was sine, then yes, we would do sine, sine x is cos x minus 90. All right. So let's start with the easiest first. VL of t is given to us. So I'm going to write out the phasor form for VL, which is 100 and phase angle 0. That's it, as easy as that. All right. VL of t is given. Take the magnitude 100, phase angle 0, write the phase. Then I need to find I. V is given to me. ZL is something I can find. So I can simply apply Ohm's law. Think back to chapter 3. If you were given the inductor voltage and you need to find the inductor current, what do you do? It's a long time ago, not that long ago. VL is L di over dt. So if voltage is given, right, inductor voltage is derivative of the current. If the voltage is given, what do you do to find the current? You integrate the voltage, right? You have to integrate the voltage. You have to solve that integration. Here, because we are using complex numbers, we can apply Ohm's law. You can solve it by applying IL is integral of the voltage over time period 0 to t. And you can solve it that way. And you will obtain the exact same answer. If you want to try it, you can go ahead and do it. Absolutely. You would obtain the exact same answer, right? VL is L di over dt. So I is integral of VL. So you can solve it by using those equations. But why do it when we can solve it by using complex numbers? IL would simply be, well, let's try it out first. V is equal to IZ. When we write these, we are talking about the phasor form or the complex number representation for all quantities, okay? So from this equation, I can write IL is VL over ZL, as easy as that. We don't need to do anything else. Does that make sense to everyone? Do you all see how easy it can be? So I need to find ZL. ZL, the mathematical operation I need to perform here is division, right? So I want my impedance in polar coordinates. If I was adding or subtracting, then I would have rectangular coordinates. But because I need to perform a division, I'm going to have polar coordinates. So I will use, instead of using j omega L, I will use omega L with the angle of 90. Omega is 200, L is 0.25 Henry. That's the magnitude. Phase angle is 90. Therefore, ZL is 50 with a phase angle of 90 degrees ohms. Easy enough. Oh, just a minute left. Okay, I'm going to continue on until I solve both example 3 and 4, so you can watch the recorded video later. If you need to leave right at 12, you're welcome to do so. So IL would simply be VL over ZL. VL is 100 with an angle of 0. This is 50 with an angle of 90. Therefore, IL is 2 with a phase angle of minus 90 amps. Therefore, IL of T would be 2 cos of omega T, which is 200T. Omega does not change. 200T minus 90 degrees. Does that make sense, everyone? Thank you. Example 4 for the capacitor is exactly the same. Vm is 100 volts. Omega is 200 radians per second. Theta is 0 degrees. Therefore, phasor VC is 100 with a phase angle of 0 degrees volts. ZC is 1 over omega C with a phase angle of minus 90. Omega is 200. C is 100 microfarads. Phase angle of minus 90. Therefore, ZC is 50 with a phase angle of 90 degrees. IC is VC over ZC. VC is 100 angle 0. ZC is 50 angle minus 90. Therefore, IC is 2 with an angle of plus 90 and amps. Therefore, IC of T is 2 cos of 200T plus 90 degrees. And that is your final answer in the time domain. All right, went to 2 minutes over time. Okay, quiz on Monday based on the material we have covered this past week. Homework that is due tonight will be pushed back. I'm going to review the homework problems. Students should be able to get most of the work done, right? We'll solve one final problem. This is example 5. I will solve that on Monday. So at the very least, the homework that is due tonight will be pushed back to Monday night. If I feel that students need little more time, then I might push it back to Tuesday. But for now, consider that it will be pushed to at least Monday night. All right, I'll be available in my office later this afternoon between 12 and 4. Also available over weekend via email, via Zoom. Yes. So let me know if you have any questions. All right, have a good weekend, and I will see you all on Monday.